Hi, everybody. Is the microphone good level for everyone? Good. All right, cool. Let's get started. So this is Sight Beyond Sight. This is detecting phishing with computer vision. To get started, I'm Daniel Grant. I'm a data scientist at Endgame. I primarily focus on malware classification and model evaluation. If you need to contact me about this presentation, about Endgame, about anything else, here's my email. I do have one request, though. Please don't phish me. That'd be real cool. I'm presenting on behalf of a bunch of other colleagues too. One project that we're talking about, Blazar, which is a URL spoofing detection, presenting on behalf of Jonathan Hiram Nanjum, and then SpeedGrapher, which is a Microsoft document phishing detection with computer vision. Bill Finlayson was the main driver behind that one. Agenda, we're going to go over a few things. We're going to do some background, like is phishing really a problem? What are the current strategies? Then we're going to dive right into the technical details of Blazar and SpeedGrapher. All right, so phishing is bad. We can probably agree on this. To push home the point, we have a nice little icon here. This is if Cliffy had a demented cousin or something. If you're more into numbers, Verizon had a really good report, data breach report. 4% of people targeted click on attachments. 94% of times it's malicious. 17% are reported, and of those, it takes half an hour on average to report it. This is mostly done over email delivery, but social media delivery has been increasing very rapidly. So there are two main types of phishing we're going to look at. One, phishing for credentials, and one, phishing for payload delivery. There are a couple other types, but if you're still getting Nigerian scam emails, that's your own problem. Phishing for credentials is mostly a bank scam or a network credential scam. It usually references a compromise or a call to action, sends you a link to change your password or to log into a site to check something out. The link often redirects to something legitimate looking, although the URL will look similar to what you're expecting, but probably not. One example of this is bankofamerica.com versus Bank of America, but with the M replaced with an RN. Completely different site, looks very similar. Next, for payload delivery, this has been in the news a lot more lately. The World Cup and Pyeongchang Winter Olympics were hit by something, and there are links at the bottom here for more information on those. The DNC and DCCC attack was based on a malicious Excel document called Hillary.xls. As a side note, if anybody has that, hit me up after this. I'd like to see how some of this works against it. These are generally macro-enabled documents that download a payload or it sends info back to a command and control server. Sometimes also links to fake software updates or fake links to download an executable. And there are a lot of strategies to do this. Since email's been around, email spam's basically been around, and so have email spam filters. They usually work on the rule of has anyone else seen this or seen something similar. If you open up Gmail and go to your spam folder, you're going to see a lot of stuff like this. Also, if you have a hosted email, like an Exchange server or any other hosted email, they often have an AV scan that checks over the attachments before it completes the email. It's often rule-based AV. So this is one I actually generated. I sent a zip file of some macro test samples to my VP of engineering. Apparently, you're not supposed to do that. So I got this undeliverable mail message back. And then there's domain blacklisting. If you're using any modern browser, they probably have a blacklist of several phishing or malicious domains. You'll see a pop-up that looks something like this, says, we're warning you. If you want to continue, you can go ahead, but we've warned you. And finally, there's training. Most large companies, especially if you have any work with the government, encourage yearly or partial yearly training, basically telling you don't click this if you don't know for sure. Ask IT, send anything weird to us. And that's cool. Those are all very useful, and those cut down a lot in the traffic that we see. But we still have phishing attacks. They're not complete. It's still a problem. So we want to try a different solution. And we want to try a computer vision solution. Why computer vision, you might ask? It's come a long way since detecting cats on YouTube. We can now detect raccoons on YouTube. We can also detect tumors in medical imaging. We can also detect stuff with self-driving cars, all this. It's all built on a lot of computer vision analysis. And in general, when you want to use computer vision, you want to be able to answer yes to this question. can an attentive user see this? So specifically for us, it's can an attentive user identify phishing? So let's see. You're all very attentive users. Hopefully you're paying attention. So let's see if anybody can see what's wrong. This is a sample email you might get. Please download the latest attachment. And you see this link below. First of all, if you're getting an email that's asking you to download a software update, be careful. Yeah. But most of you are also pointing out that this B looks very different than the normal Adobe B. In the international domain name system, several top-level domains are accepting extended character sets to work with different languages. So this could be a valid domain, while not being the Adobe site, and you're likely getting yourself into trouble. Another example, we have a Bank of America login website. You probably immediately see bofamerica.co.cc. That's not very good. You don't want to log in. You don't want to put any credentials into this. Another one, say you open up a Word document. You see this. What should first key you off is the entire thing. This is all bad. What next should key you off is this enable content button. Or it's not even a button, it's an image telling you how to enable content. Of course, what a lot of you saw and what I saw first was the macrosis. That's pretty bad. So let's go ahead and dive straight into some technical stuff. We're going to talk first about Blazar, and it's a URL spoofing detection. Our fancy name for it is detecting homoglyph attacks with a Siamese neural network. So what is a homoglyph attack? Let's break the word apart. Homo, same glyph, character. It's an attack that exploits the visual similarities of different characters. So you have something like Amazon with an O and Amazon with a 0. We're also including in this class, for the sake of this project, extensions or subtractions to strings. So you could have time.com, times.com, google.com, and Google with just one O.com. You see a bunch of examples here, like Microsoft and Bank of America. That email that I showed you before with the weird B in Adobe, that's an actual attack from September last year. And it was to deliver the beta bot Trojan. Malwarebytes has a really nice blog about it, so check that out when you get a chance. So yeah, the weird B. One way to sort of solve this problem is to use edit distance. And this is generally counting the number of insertions, deletions, and substitutions in a string. So for example, we have Amazon, we substitute an O with a 0. We time, insert an S, Google, remove an O. This spoof for Microsoft, we do 2 substitutions, so it's edit distance of 2. This Bank of America, we do 1 substitution and an insert, edit distance of 2. You can probably immediately see how this could blow up if you're using non-ASCII characters or extended character sets, especially if you're using like UTF characters or Unicode. You can create a string that looks almost identical to bankofamerica.com using completely different characters, because there are several characters that you really can't tell the difference between the B that's Unicode whatever and B that's Unicode like 6,000 something. So the edit distance of that would be like 14. But it would look very similar. One way to mitigate this is an improved edit distance. And so this is to weigh the edit distance of the characters based on their visual similarity. You can see this on single characters. A 0 and capital O, very similar, high weight. Double characters, RN and M, very similar, high weight. You can see stuff like 3 and E, not very similar, low weight. And so when you combine the edit distance with a weight, then you can create a sort of closer score to how much this looks similar to another string. Problem with this is just a combinatorics issue. If you have to map out the similarity of every character, well, I don't want to do that. I don't know if anybody does. You'd probably end up using some sort of visual learning system to do that, and if you're going to do that, you might as well go the whole way. So our technique is going the whole way. We're going to convert text into images and then to feature vectors. And we want these feature vectors of potential attacks, potential strings that look very similar but are different. We want those to have a small Euclidean distance. We want them to be close together. And we want strings or feature vectors of strings that don't seem like attacks. Google versus Facebook, that's not an attack. We want that to have a large distance between it. And as a point of operation, we're going to be doing this on tens of thousands of items. And you don't want to look through, you compare one feature vector to tens of thousands of other feature vectors linearly. So we're going to put it indexed in a KD tree so we get faster lookups. So first thing we need to do is create a sample set. We need to create spoofed training set. So we have Google, and you can do whatever you want under the sun to create different sort of spoofs of Google. Add some O's, replace characters, use swaps of uncommon characters, that sort of stuff. And you do that with a bunch of different data sets. So you have a group of things that look like Google, a group of things that look like Facebook, a group of things that look like ESPN.com, whatever. You have a whole set of those. And then we're going to get into the neural network part of it. And we're going to use a convolutional neural network to learn the qualities of an image. Now, convolutional neural networks are very popular in image recognition because they have the ability to sort of learn shapes and characters of shapes and forms and all that sort of stuff. The way that they basically work, and we could spend over an hour talking about this, so basically how they work is you have a sliding window around the image, and each of those gets a series of convolutions to it. So you can try to learn this looks like, or to have a convolution that tries to pick out, this looks like a left-handed curve. This looks like a line on the right side of that square. This looks like some other shape. And then you build up layers of that so you can start to learn more complex shapes. So eventually, after you've trained something, you can run it through, and it's basically saying, okay, this is a circle on top, and there's a square underneath it, and there's this other stuff. So it can learn shapes and their relation. And then finally, to put this all together, we're going to use it in a sort of Siamese neural network training form. So we're going to try to convert the images to feature vectors. So we have that network that we created, and this was this network on the right side here. This is the actual one we use. It's pretty textbook. It's a convolutional layer, a max pool convolutional, max pool flatten, and a dense. If you look up, 101, how to do a convolutional network, that's sort of the one that it'll pick out for a first try. So we're going to try to do it in a Siamese fashion. And what this means is that we're going to take pairs of inputs and run them through the network to get pairs of features. That's the Siamese nature of it. When we have those pairs, we want to compare them. If they're in our spoof set, we want the distance between them, the Euclidean distance between them, to be low, close to 0. If they're on a non-spoof set, we want that distance to be 1, so high. You can think of the network, that big square in the middle here, as sort of a functional programming thing. You throw an image at it, and it spits out an output. If you don't change anything, you throw the same image through it, it spits out the same output. Different image, different output. But we want to keep on training it so it learns, things that are spoofed are close together, things that are not are far away. And we do this through a method called backpropagation. And that's basically, if you're wrong on your prediction, you say, like, we have Google and Google.com with 3 O's, and the edit distance is, or the Euclidean distance is high, then you're going to change all the weights up in your network, backpropagate the information all the way up there, and change them in the direction so next time it ran that through, it would say they were lower. And you do this on tens of thousands, hundreds of thousands of samples, and then you come up with a trained network that does what you want. And so we want to see if it actually does work. So our network is putting out features that are in a 32-dimensional feature space. I don't know about y'all, but I've never been very good about visualizing 32 dimensions. So what we commonly use is a technique called PCA, Principal Component Analysis, and that sort of squashes the features down into a 2-dimensional space so we can look at it. And then here we can actually see how our features compare to each other, where they are in relation. So in the bottom right-hand corner, if you can see the icons, this shows all of the Google spoofs. And they're all clustered sort of close together. They have a small distance in between each other. And you can see some of the other clusters correspond with Facebook, Twitter, Snapchat. And the clusters themselves are far away from each other. So this is doing what we expect, what we hope it to do. Items within a spoof, close to each other, small distance. Items outside of a spoof, then they're far away, large distance. So that's working well. So in practice, how we want to do this, we've got a trained network that can discriminate between two strings that look alike and two strings that look dissimilar. And we want to seed it. We want to populate the network with URLs that we want to protect. So we get a list of common domain names. You can get the Alexa top 50K, top 100K, anything like that. And then you convert them through our network into feature vectors, 32 floats. And then you index them all in a KD tree. So when you want to check something against it, you can take that string, turn it into an image, and then get the feature vector for that, and then query that through the KD tree to see if it's close to anything in the tree. And if it is, and if it meets a certain threshold, then you can say, okay, we think this might be a potential homoglyph attack against Google. In general, when you have all these techniques, you want to be able to compare them to see how they do against each other. One method of doing that is just comparing the accuracy, but the accuracy depends on the threshold that you choose. You pick a threshold of 0.9 for your thing, you'll have one accuracy, 0.2, you have a different accuracy. And each thing is going to sort of have a different curve associated. So what we use instead is a ROC curve. A ROC stands for Receiver Operating Characteristic. It has a weird name because it was developed in World War II to measure the efficacy of radar operators or something. But what it basically is a measure of the false positive rate on the x-axis and a true positive rate on the y-axis. So let's say you want to be very aggressive in your detections. You'd want a high true positive rate. That, although, corresponds with a high false positive rate. So you'd be on the right side of this graph. And you'd detect a lot of stuff. You'd detect a lot of true positive, things that are actually malicious that you say are malicious. But you're going to get a lot of stuff wrong. You're going to say a bunch of stuff is malicious that's not. On the other side, if you want to be conservative, you'd be on the left side, and you would have a low false positive rate. You wouldn't call anything malicious that wasn't, but you're going to miss some actual malicious stuff. In general, though, measuring the effectiveness of your entire algorithm, you can measure the area under the curve here. So you can see this diagonal line. This is just for reference. This is this represents a 0.5 area under the curve. And that's basically you'd have a coin flip on every sample. 50% chance it's right, 50% chance it's wrong. We can see that the edit distance method got an area under the curve of 0.81. Not too bad. Visual edit distance did some good improvement. It got up to 0.89. And our Siamese neural network got up to 0.97. Generally, that's a pretty good result. Generally, you want to be your curve to be at the top left corner. If you can get all the way up to the very top, you have area under the curve of 1. You've solved that problem in the constraints that you formed it. So that's most of Blazar. There's a lot more information about it that we can't cover in the time period here, but we have a repo on our in-game public GitHub titled Homoglyph. You can check that out. And we also have a paper published on Archive. We're also in the IEEE security paper or security journal. I don't have the link for that, but I can find it later, but that was presented just a couple months ago. Next, let's go into SpeedGrapher. SpeedGrapher is detecting macro-enabled Microsoft Word documents document phishing using computer vision. So we're trying to detect phishing documents. Since we're using a visual approach, let's define the problem visually. We basically want to detect the item on the left as malicious. This is saying, oh, this was made in a newer version of Office. You need to go enable content, because surely that's fine. Versus the item on the right that is just some graduation statistics or something. It looks pretty normal. And with most computer vision applications, this is going to be an ensemble of a lot of different techniques. Computer vision in general is a sort of intimidating topic to try to jump into from not knowing anything. I want to try to demystify that a little bit, lower the barrier of entry, because a lot of this is a bunch of techniques that aren't too complicated in their own right, but you combine them to make something bigger. So we're going to try to look at the prominent colors of an image, the blur and blank area detection, optical character recognition, and icon detection, which is a really cool project. So first things first, we need to get some images. We want to get the image of the first page of a file, because that's usually, if we're detecting this sort of stuff, that's usually where somebody's going to say, hey, can you enable macros, do me a solid? Instead of opening the actual file and screenshotting it, which is a slow, potentially manual approach, you might be able to automate that somehow, but it just doesn't really seem like an elegant approach. We're going to get the preview from the Word interop class. This is some documentation from Microsoft on it. It's pretty straightforward. it just sort of opens it up under the hood, snapshots it, and sends that back to us. And a note on safety. It's still worth sandboxing. Before we were dealing with strings. Strings don't really hurt you that much. Now we're dealing with actual malware. So disable internet, disable macros, enable Windows exploit guard, do all those sort of things. Don't add docx to the end of your file, so you won't even open it if you don't try. So all this stuff is good. Keep sandbox, keep everything safe. So let's go into the features that we want to get. First, we want to try to get the color clusters, and we're going to use k-mean clustering in the RGB space. So let's start with, we have an image like this one. All this image is a series of pixels. Each pixel has a color combination, red, green, blue, or whatever color coding scheme you want. We can take all these pixels and just map them into the RGB space. So if we had, say 100 of these pixels, it's way more than 100 pixels, let's say 100 pixels, if 95 of these pixels were all white, then you'd have a lot of dots at this space of 255, 255, 255, which is the color code for white. If you had a bunch that were black, you'd have a lot of dots at the space 000, which is the color code for black. So you map it in this space, and then we want to try to do a clustering algorithm. And so k-means clustering is pretty simple. K is just the number of clusters you want. So this is the predefined parameter. And we're going to pick 3 for this case. So we want 3 clusters. And in the space that you're looking, in your feature space, you pick 3 random spots. And then each of those you run down the algorithm to say, what data do I have that's closer to this cluster center than anything else? And that becomes part of that cluster. And then you reevaluate, you recenter that cluster based on the data that was just glommed together with it. And so that changes them, moves it closer to where that actual cluster center was, moves everything around. Eventually, you keep on going over this a little bit, and eventually you get to a sort of steady state, or you've run the maximum number of steps that you want to do. And then you have an area that sort of identifies the maximum, the biggest clusters that correspond. So in this instance, we take this image and we convert it to just a color feature. And we can see that most of the color is white, about 95, 97% or something. There's a good bit of yellow. And then there's the rest of this, which is just sort of a combination of the black and red and every other color in there. So we can see we now have a feature, a numerical feature for the colors that comprise this document. Next, we want to do blur detection. And what we're going to do is the variation of the Laplacian. And that sounds real fun, right? Those of you that have experience with calculus, if you remember back, this might sound somewhat familiar. But this is basically the second-order derivative. A Laplacian is a second-order derivative. So it measures the sharpness of change. If you think about it in terms of distance, velocity, and acceleration, classic example, velocity is the measure of change of distance. It's the first-order derivative. Acceleration is the measure of change of velocity. It's the measure of sharpness of change of distance. So it's the second-order derivative of distance. If you look at a document, if you're looking at just a line of pixels in grayscale, if you have a white pixel and then a black pixel and then a white pixel, you're going to see that's a very sharp change. That's going from 0 to 255 and back to 0. That's pretty quick. If you have a white pixel and a little bit of gray, a little bit of gray, black, a little bit of gray, a little bit of gray, white, then you can see that's a smoother change. It's going to have a smaller Laplacian, smaller degree of change. So we can use that to measure blur, which is basically that concept. It smooths out the pixels so you don't really see it. A lot of malware does this. It's like, oh, this is a secure document. You need to enable macros to see all this hidden stuff in between. This is just an image. There's nothing hidden beneath it. It's just a blurred image. So this is one detection that we can do there. Oh yeah, and if you don't care about calculus or physics or any of that stuff, OpenCV makes a one-liner for you. You just implement that and you call it a day. Next, we want to do blank detection. And here we want to calculate sort of the mean, the variance, and the max of the average RGB space. So these numbers don't necessarily correspond to any one color. This is just sort of the average of those three numbers. We're just trying to like convert this into something numerical. So you can see on this image on the left, we've got some colors, we've got some white, we got some black. The average of the mean is somewhere in the middle. You have a little bit of variance. You have a max. You have a white in there, so the max is 255. If you look the image on the right, just a blank document, the average is 255. It's white. The variance is 0. It doesn't change. The maximum is 255. It's white. So that's, you can see like that's a blank document. You could also do this for other color. If you have blue, the mean's going to, if everything was blue, the mean's going to be some number, the variance is going to be 0, and the max is going to be that first number again. Everything's blue. You're just looking for basically a 0 variance and then a color code associated with it. And then next we're going to do text detection. So one of the tricks people try to get around some of the rules that are used in some of the previous macro detection stuff we talked about is to have an image instead of text. This helps avoid detection because if you're looking for a keyword, you're not going to find that in an image. But they can still give you instructions on how to enable macros and all that sort of stuff. So to do that, we're going to use optical character recognition. This is a pretty well-worn topic. We're not going to go very far into details. Suffice it to say, Google Tesseract's pretty good. We use UWP OCR, which is native in Win 10, so that was helpful for us. As an added bonus, you can also put in text translation, which is another fun machine learning project. You can try to implement it yourself. That's workable in a small scale, but really Google, Bing, any search engine has an API. You can just send text to, it'll auto-detect the language and convert it, and that's a lot easier than spending your Saturday trying to create a text translation engine. Believe me. And then finally, this one's really cool. We're going to do icon detection, and we're going to do it using this this method tool, this whole set of stuff called YOLO version 3. And yes, there was a version 1 and 2. There's also a version 9000. They jumped from 3 to 9000. I don't know. So in this instance, YOLO stands for you only look once. And this is different from most other object detection frameworks where they typically, try to find the object you're looking for, then try to find a bounding box that looks good, and then iterate on that several times, going back and forth over the image until it feels confidence. This one is instead predicting the class, so trying to predict the class of the image or the object you're looking for, and the bounding box around it at the same time. This guy, PJ Reddy's really funny. Go here, look at all the tutorials. It's really good. Read the paper. It's also really good. I recommend using this. This is the most complicated thing in this entire presentation. I'm going to try to explain some of it, but they'll do a better job, honestly. So go check that out. But in general, you take the image, you break it up into cells, and each cell is going to have a probability of matching a class. So say we're trying to detect this this window flower thing, whatever that is. We're going to say this cell that's highlighted has a probability of being that window flower. And then each cell is going to have its own probability of being whatever class you're looking at. And then at the same time, it's detecting possible boxes for all sorts of images throughout the thing. And then it compares those boxes with the probabilities that are previously calculated for each cell, and then comes up with one box that has a confidence of being something that you're looking for. So to do this, we're going to take 5 icons that we want to detect. Most of the time when this sort of phishing occurs, people are trying to convince you that they are Microsoft or they are instructions from Microsoft. So they're like, oh, this is a Word logo. You should trust us. So we're going to try to detect a Word logo and enable content and all these different Office logos that they have. And to do this, we're gonna take about 100 or 1,500 samples and label them using a bbox label tool. We'll show a tutorial, a link to a tutorial on how to do that later. It's really easy. And we're also going to do some augmentations. We're going to do some color shifts and some resizing just to make this more robust to changes. So in general, you have all of your documents, all these pictures that you've picked up, and you put them all in a folder. You direct this bbox tool to that, and then it pops up an image and tells you draw a box around what you want to detect and label it. It's very simple, very straightforward. This is just a way of taking this information and turning it into textual information. So, boxes, these boundaries on this image, this label. One thing you might have stopped me at, especially if you heard the previous talk on machine learning and deep learning, is you have 1,500 samples in 5 classes. For doing anything with neural networks, that seems like very few samples for that many classes. And you would be right. But we're using something called transfer learning to sort of bootstrap ourselves. And transfer learning in this context is taking a network that's been pre-trained on a general task, a larger general task, and then taking that pre-trained network and retraining it to specialize in the class that you're looking at. The example here is we take a pre-trained network that was trained on a ton of ImageNet data, a ton of images, to detect many different classes of things. So like we were talking about earlier with the convolutional neural networks, it's already learned to detect, okay, this is a curve, this is a circle, this is all these other little features, shapes, and all that sort of stuff. And we're just saying, yeah, we want that shape, this color, and then narrow that down and say, that's this class. In general, you can think of this as if, say you were good at racket sports, you're good at tennis, you're good at racquetball, all this sort of stuff. You've learned some depth perception, you can see the ball coming in, you've got hand-eye coordination, you've learned the muscle memory of this twisting motion, and then say you wanted to learn baseball, you wanted to learn how to be a batter. You have a head start because you have all these things, you just need to specialize into using those skills to hit a ball. So very easily, you learn Kung Fu. So specifically, the way that we're actually doing this, we're using the darknet port for Windows. You can check out here, pre-trained data set. It's a port for YOLO that works. It's all cool. And then follow this guide to label samples and train. It's very easy. It's sort of point and click sort of stuff. Under the hood, it's very complex. You can read lots of papers on it, but the application of it is pretty easy. And computer science is all about abstraction anyway, so just go ahead and abstract that away. And I'll have all these links at the end too if we miss them. And then, so the end result is we can throw an image at this network and it can identify these different office icons, these enable content sort of buttons. And you'll notice that it detected the button here, but also detected the text enable content. So it learned the letters that it was supposed to look for as well. So now we have all that info. We have a sample, we have the blur and blank detection, we have the colors, the centroid colors that we have and the size of those centroids. We have the YOLO information that gives sort of the percent that we think each of these icons are, or the percent confidence almost. And then we have the OCR text, translated OCR text even. So now it's time to build a classifier. So we've got features, that's cool, but the next step is getting labels. This is a hard part of machine learning, is getting clean labels. Nobody just gives them to you unless it's a toy data set. Luckily, it's time for the shameless plug. We just released malware score for macros into VirusTotal. I feel comfortable doing a shameless plug because this has been the last 6 months of my life. I was the primary developer on it. And this is a machine learning based maliciousness detector that looks at the macro text of a document. And actually, SpeedGrapher's original purpose was finding true positives for this, so we could improve the score here. So go check that out when you get a chance. But we're going to use that as the ground truth of labels. So next, we're going to build a dumb classifier. And I'm going to say it's a dumb classifier because in our operation, we haven't really built a classifier for this. I built this for this talk. We're still in the process of refining more information we can get for SpeedGrapher, extending it to different file types, all that sort of stuff. So we haven't really gotten to the classifier thing. But I want to show you how when you have rich data, really good data, and decent labels, then you can build something very robust very easily. And so what we're going to do is just take all that data that you saw in that JSON blob, just smash it into a vector. We're not going to do any analysis on it, anything like that. We're just going to put the raw numbers in there. So we take the color centroids, put those in there. We take the blur and blank vectors, we put those in there. The YOLO keys, we rip out the percentage and set them in the appropriate index level, put them in there, and we grab some text keys drop them in there. This is one hot encoded. If it's there, the value is 1. If it's not, the value is 0. So if you had just enable content in text, you would have a vector of 1, 0, 0 because it didn't have enable macros and it didn't have macros. If you had enable macros in the text, then you'd have 0, 1, 1 because it had enable macros, and also macros because it had enable macros. So we have that, and we just put them all in a vector. I don't care. So one thing you do want to care about, though, later we're going to be using a random forest classifier, so this doesn't really matter. That's a quirk of the classifier. It's tree-based, decision boundary-based classifier. But in general, good data hygiene to always do is to normalize your vector between 0 and 1. You want to make sure that just because one of your features has a large scale, 0 to 9,000 maybe, you don't want that to overweigh another feature that's scaled 0 to 5 just because it has big numbers. It might not have big importance. So we're going to normalize this real quick. Convert it to NumPy vectors. If you don't use NumPy and you're doing data science, you're probably doing something wrong. So use that. And then we're going to build a classifier. And for this, we're just going to make a basic random forest classifier. This I just copy and pasted from Sublime Text, so this is more complicated than it needs to be because this could be one line. You just import import like random forest classifier from Ensemble, and then say number of estimators and max depth, and you're pretty much good. You have a classifier that you can train now. And then finally, we want to train it. One important part of training, and this should be hit home all the time, is you don't test on the data you train with. This would be like if you were getting ready to come to Vegas and you were practicing blackjack, and you look at your cards, and then you look at the dealer's cards real quick, and then you make your bet. That might work at home. You're going to do great at home. You come here, you get kicked out of the casino. Here, you want to train on a certain set of data and test on another set of data. But you want to be able to do this like at scale. So what we do is what's called k-fold cross-validation. And this is training on a portion of the data, testing on another portion of the data, and repeating with a different train and test set. So for this instance, we're going to do, say we do 10-fold cross-validation. We're going to run this 10 times. We're going to take a test set size of 10% of the data. We're going to train on 90%, evaluate on the 10%, record all the predictions that we made on it, and the valid scores, the true positive scores or the true scores of that. And then we're going to repeat that, but we're going to move our window, and we're going to test on the next 10% of the data and train on the rest of the 90%. And we keep on doing this and aggregate all of these testing points of information. And then we can create a confusion matrix. We can create false positive rates, true positive rates, all that sort of stuff. And we can create that ROC curve that we did before. So let's take a look at this. And again, you can plot in one line right there. You might even miss it because we're that good. We're up here. We have a receiver operating characteristic of 0.98, which was really good for a dumb classifier. That's a testament to good data going in. We can look at the false positive rate and the true positive rate. We have a sort of class imbalance of malicious versus benign in our training set. That's sort of okay. This isn't too bad. If you have like 100 benign samples and 20,000 malicious samples, you got a problem. This one I'd want to adjust, but for the sake of this, it's fine. And then we can look at our false positives. We have some samples that we label as malicious, but are actually, based on our labeling system, are considered benign. And we have false negatives, things that we label benign, that based on our labeling system, we label malicious. So it's always good practice to dive into those. You want to look at what you miss, and then you can tweak and adjust how you perform, change your algorithm, change your data, change your labels, and then retrain it and just minimize those two functions. So one thing that was very interesting is 70% of the false positives are actually neutered malware. So we see something like this. This is one of those samples, and that looks very clean and all, but it is fishy. It's asking you to enable content to view a decrypted message. When you look at it in VirusTotal, you can see like the actual macro text or if you have a parser that can rip it out or something, you'll see that macro code was removed by semantic disarm. Like, thanks, semantic. That's good and all, but you messed up my classifier. And also, the majority of the false negatives are malicious but don't really show it. So we're doing a computer vision application. Some things aren't applicable for computer vision. This has to be part of a layered mechanism. You can't just depend on one thing. That's usually a tenet all the time. So some of these just don't look bad. Some are in characters that our OCR has trouble with. We didn't really do much configuration on the OCR. We could revisit this when we decide to, but a lot of Asian characters just don't show up for us. I think we were just using a Latin character set or something. And some don't show it on the first page. We have this nice resume by Joe Smith. Joe, if you're here, come talk to me after class. This is a security specialist, but if you dig into the macro there, that doesn't look like it's doing anything good. So while it looks like a normal resume, our computer vision application isn't going to detect it because I wouldn't want it to detect that because it doesn't look like it's bad. We're trying to find stuff that looks bad. Luckily, our other malware score caught this one, so we're all good. And so that's basically it. We're at about 40 minutes right now. We covered the background, if phishing's a problem, current strategies. We talked about Blazar and SpeedGrapher. And here's a set of links if you want to take a picture of. If you got any questions, I think we've got a microphone that we can pass around. And yeah, that's about it.
Well, thanks a lot, Daniel. So if there are any questions? Yeah.
Your ROC score was phenomenal, 0.98. It almost makes me a little skeptical. So what did you do to defend against overfitting?
Yeah, so overfitting is definitely a problem. For this, since we're using cross-validation, that's a decent measurement technique against overfitting. There is, and I will say there's an intrinsic problem with this data. There are repeats throughout. And so we might be training on something that looks super similar to something we're testing on. That's a huge caveat, and it's a very good point. This is something that we want to try to, when we are going to build a real classifier for this, we want to sanitize and deduplicate all of this. But that being said, a ROC curve of over 9.8 in this realm is not unheard of. Our macro detector is over 9.9. It's almost at 4 nines. We're trying to get that fourth 9.
Any more questions?
Yeah. So on the Blazar project, did you guys try to use different font types? Because I can see how different font types would change the look of the URL.
That is a very good question. We didn't. That's sort of on extended research if we want to really develop this into part of the product. We used Arial as the font base, and with the repo, we asked you just to download Arial and install that one because that's what it's worked on. But yeah, using different fonts, it should be trivial just to add a different font and expand your data set, duplicate your data set based on that. You might lose some accuracy, but it should work the exact same way. But this was a research project that we did. We haven't put this in the product yet, so we just used one font for this one. But that is a very good question.
For Blazar, let's say you're trying to visit goggle.com, like you actually want to go to goggle.com, but is there any way to really make sure that it won't detect or try to train it so it won't flag legitimate but similar looking websites to like Google?
Yeah, so that's a very good problem. One way that you want to do this is expand your training data set to include things that are similar. You are going to have you're never going to get this method to work 100%. I'll say it right there. We also use this for file name detection. If you're running a bunch of processes, we had like SVC host. If you replace O with 0, that's malicious. But you have stuff like Java and Java C. Those look like they should be spoofs of each other, but they're both legitimate processes. So when you have small character strings like that, you do have a lower rate. And you'll notice that our false positive, if you let me go back all the way here, let's see. Our ROC curve sort of bottoms out at one point, and this is exactly the problem that we're seeing there. 1 second. Yeah, you can see at the top we're not getting we're getting pretty close, but it does bottom out a little bit. We have, when we're doing the one for file type, it's even more pronounced. This one's a little bit hard to see, but file type, it sort of starts here and then jumps up because you're having those characters that are legitimate but look like spoofs of each other. So that might be a whitelisting feature that you add to that. Like, okay, you can allow Goggle, it's fine. Yeah.
Any more questions? Well, that's grand. So thanks a lot, Daniel.
Thank you all.